Well, the second part of this section is the quotient rule for derivatives. And of course, quotient means fraction. So this is about how do we take the derivative of a function that is a fraction. And you see it stated here, if f of x is the fraction u of x divided by v of x, then the derivative of f prime of x, is equal to a fraction that's rather complicated. V times u prime minus u times v prime, all divided by 2. Those are prime. So that's v times the derivative of u minus u times the derivative of v, all over v squared. Or written in the notation that we've seen as nu, that is the derivative over u times v. It's still the same result, it's just written out differently rather than saying f prime, derivative of the fraction of u over v. Now notice a different order than what we had for the product rule. Remember, in the product rule, it was the first function times the derivative of the second plus the second function times the derivative of the first. But here in the numerator, it's the denominator, which you could almost think of as the second function. It's the denominator times the derivative of the numerator. V is denominator, u is numerator, minus the denominator. Oh, I wrote that backwards, didn't I? Oh, my bad. I just noticed a mistake here. It's minus u, that is the numerator, times the derivative of the denominator there. I wrote it correctly in the first line, but incorrectly in the second. I apologize for that. So let me rewrite this whole thing. The derivative of the fraction u over v is a fraction where the numerator of the result is denominator times derivative of the numerator, subtract numerator times derivative of the denominator. And the denominator of this result is the old denominator squared. Okay, my bad. So you see that we do it in a bit of different order, and so it requires some concentration. This is a relatively complicated rule to use, and so we have to be very careful of using it, and we don't want to use it when it's not necessary. Let's look at our first example, though. Okay, in this case, we're given that the function f of x is the fraction x minus 1 divided by 2x plus 3. And we're to find f prime of x. We're to find the derivative of f. Now, we recognize, I think, let me write it down here where I can point. We recognize, I hope, that in this setup, the top function is the u, that's the numerator, and the bottom function is the v, as goes by that formula. And so we're thinking here in this fashion. To find the derivative, we use the formula. The formula says, oh, well, the derivative is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator being squared. So as we begin our process like we did with the product rule, we name, we name the numerator, that's the top. We know that's x minus 1. And we know that we'll need the derivative of that. And by now, I hope we recognize the derivative there would just be 1. The derivative of x is 1 minus the derivative of 1 is 0, so 1 minus 0. And then we recognize that the v is the denominator. That's just 2x plus 3. And we know that we have to, for the formula, we have to know v prime, the derivative of v. Well, the derivative of 2x is just 2, and the derivative of 3 is 0. 2 plus 0 is 2, of course. And so now we're ready to do our substitutions. F prime of x. We create the fraction. Well, v is 2x plus 3. Make sure we put the parentheses around it. And u prime, that resulting derivative, is just a 1. And then we subtract u, which is the x minus 1, and multiply with the derivative of v, which we saw is just 2. And then we take the original v, which is the denominator. The denominator here is the old v squared. So it's the 2x plus 3, but we have to square it. Now, what we need to do from here on out is to perform algebra and simplify this result. I mean, more or less, we found the derivative, but it's just not in simplified form. So that's what we have to do. Now, simplify. Now, I will kind of take the approach that I'm going to show you here. Of course, 2x plus 3 times 1, there's not any question that just gives us a 2x plus 3, right? But anytime I have a negative sign and things multiply together, to keep from being confused, I'm just going to reorder the way I have this x minus 1 times this 2. And here's my minus, and I'm going to put the 2 in front and then the x minus 1 in back. And of course, that's all over 2x plus 3 that's being squared. Now, that setup just allows me to recognize that I'm really multiplying with a negative 2, aren't I? So that rearranging that makes it easier for me to think of and will probably put me in a position to make fewer mistakes. So we have the 2x plus 3, and when we multiply negative 2, we'll get a negative 2x, and then negative 2 times negative 1 is a plus 2. And of course, that's all over 2x plus 3 being squared. And then we continue to look at that numerator, and we notice that we have a 2x and a minus 2x, and so that's just going to leave 5 in the numerator. So the derivative f prime of x is simply going to be the fraction that has 5 in the numerator and 2x plus 3 squared in the denominator. And we've successfully applied the quotient rule to this function. We'll look at another problem on the next page. Here in our second problem, second example, we have a function that's a fraction. It's a little more complicated this time. It's stated as y is equal to, and we're to find derivative of y with respect to x, or dy over dx. So let's just kind of state again what we know we're doing is when we work on this, the derivative of y with respect to x is, now I'm going to write it in letters, but let's understand I'm actually saying numerator and denominator. So the derivative of a fraction is the denominator, which we called v before, times the derivative of the numerator, minus the reverse of that. That is the numerator times the derivative of the denominator. And we called u and v before, remember, that what we did before, we're thinking as the top, that is the numerator as a u, and the bottom as a v. So that's what I'm referring to when I talk over here. And then we divide all of that by the denominator squared. So that's what we're going to be working on. I'm not going to do them separately, though. That is, I'm going to write out in calculus notation what it is we're going to do, and then we'll just take the steps to go through it. And so here's what I mean. In this formula, we start out with the denominator times derivative of numerator. So we're going to have a relatively big top to this. Let's see if I'll see how far I'll need to go. We're going to say the denominator, which is negative 3x plus 2, times the derivative of, I'm not trying to calculate, I'm just trying to write. So the derivative of the numerator. And of course the numerator is 2x squared minus 4x plus 3. And then from that we subtract. And we go in the reverse order. That is, we say the numerator, which is 2x squared minus 4x plus 3. That's just nothing more than u from above, is it? Times the derivative of v. V is the denominator. So times the derivative of the denominator. Well, there's the derivative of, and of course the denominator is negative 3x plus 2. So I haven't done any calculation of derivatives. I'm just writing in that's what I need to do. And then the denominator of the result is the old denominator squared. So it would look like that. Okay. Now let's continue. That is, the continue is, let's actually calculate the components. That is, let's do the derivatives and put them in. So we have negative 3x plus 2, and then we're going to calculate the derivative of 2x squared minus 4x plus 3. Of course, the derivative of 2x squared is 4x to the first, minus the derivative of 4x is just 4. Right? So we have minus 4, and of course, plus the derivative of 3, which is just 0, so we don't write that in at all. Minus the 2x squared minus 4x plus 3, and now times the derivative of. So we're calculating the derivative. The derivative of negative 3x is the number negative 3. The derivative of 2 is 0. Negative 3 plus 0 is just negative 3. And then all of that is being divided, of course, by negative 3x plus 2 squared. I'm going to do two things before I complete this. That is, actually, I guess I'm going to do one thing. I'm going to put this negative 3 in front before I multiply. It will make it easier for me to think of. So I've got negative 3x plus 2 times 4x minus 4. Those brackets were to help me look later on. When I see a bracket, I know that that's the result of finding a derivative. And it kind of gives me a way of helping me review my notes. Now, if I put this negative 3 in front, I'm going to have a negative of a negative, which will be positive, won't I? And then I'll have 3 times the 2x squared minus 4x plus 3. So just a little rearrangement before I actually calculate. And of course down here I have a negative 3x plus 2 squared. Now, some of this I can do in my head and other parts I can't. So I'm thinking over here on the side, I need to know how to calculate negative 3x plus 2 times 4x minus 4. And of course that's going to be a FOIL operation. So I'm going to get a negative 12x squared when I do this multiplication. And then I'm going to have a negative 3x times a negative 4, which will be positive 12x. And then I'm going to have a 2 times a 4x, which will be a plus 8x, and a 2 times a negative 4, which will be a minus 8. You see we get a negative 12x squared plus 20x minus 8 there. So we'll substitute that in, of course. Now that was that first product in the numerator, wasn't it? So I have a negative 12x squared plus 20x minus 8 to replace this part of the fraction. And then when I do the multiplication over here on the right, the 3 multiplication, I'm going to get a 6x squared minus a 12x plus a 9 as I multiply that out. And the denominator is still negative 3x plus 2, the quantity squared. Now, as I look above, I'm thinking I will be able to combine some terms there. And so I see that, yes, I have a negative 12x squared and a plus 6x squared, which is negative 6x squared. That's kind of taking care of these two pieces, hasn't it? And I've got a 20x and minus 12x, which is going to be a plus 8x. That's taking care of these two pieces. And then I have a negative 8 plus a 9, which is a plus 1. And I still have negative 3x plus 2 squared in the denominator. Now, there's always a question about our answer. When we have a fraction, can this be reduced? And normally the way we would answer that is that we would take the numerator and factor it, take the denominator and factor it. Well, the numerator is factored, the denominator is not. So we might have to go to the trouble of trying to factor that numerator. But let me suggest to you, in this case, we can come to a conclusion more quickly. Because notice with the last term, the constant term of that numerator being a 1, if we were to factor that, I mean, just think about this. If we were to factor that, what we have in this position and what we have in this position has to multiply, say it has to multiply and give a 1, it would have to get a 1. So that would mean both of those would have to be a 1, wouldn't it? And if we look at the denominator, we don't have a factor that has a 1 as a constant. So we can tell right now that this will not be reducible without even having to do any factoring. And so that would be our final answer for our derivative. Continue our discussion of the quotient rule. This is about the place where I normally tell students, I hate the quotient rule. Now I do that, of course, to make a point. I don't really hate it, but as you see, it's a very complicated rule, and we do have to memorize it. It is something that we need to know, and we'll have to use it on test number 2, and we'll have to have it memorized by that time. But if we can get away without using it, we would like to. And so here's one thing I want you to remember, and then we'll look at some examples. Just because we have a fraction, just because we have a fraction, doesn't mean that we have to use the chain. The fraction doesn't always mean, I should better put it that way, doesn't always mean that the quotient rule is required. Now, sometimes it does mean that, okay? Sometimes if we have a fraction, the only way to find the derivative is with the quotient rule, but not always. So here would be an example of what I mean. Let's say example number 3 here. If f of x is, say, 5 over x to the 2nd power, then find f prime of x. Now this is a quotient, and so the quotient rule could be used. Okay, the quotient rule could be used, but it's complicated, isn't it? Okay, well, if we were to use it, let's see how that would go. We'd have f prime of x is equal to, okay, and remember the way we do this. It's the denominator times the derivative of the numerator. In this case, the numerator is 5, minus the numerator, which is 5, times the derivative of the denominator, and the denominator is x squared. And we take the old denominator, which is x squared, and we square it. And so using the product rule here is the quotient rule is a little bit complicated. We already knew that. Now, here is something, though. We have x squared times the derivative of 5. But 5 is a constant, so that ends up being x squared times the derivative of a constant is always 0. Now, we have minus 5 times the derivative of x squared, and of course we know the derivative of x squared is just 2x. And of course we recognize using our rules of exponents, when we square x squared, we multiply the exponents 2 and 2, so we get x to the 4th. And then when we begin to simplify further, of course, x squared times 0 is just 0. So in the numerator, we just have negative 5 times 2x, which is negative 10x. And in the denominator, we have x to the 4th. And then, of course, that is simplifiable because an x in the numerator will cancel with an x in the denominator. So we'll have a negative 10 over x to the 3rd power. So it simplifies in that fashion. Now, here's what I mean that we don't always have to use the quotient rule. It works, but we could do this another way. Alternate method in this case. We can't always use an alternate method. We first could say, look, why don't we take this f of x function, which is 5 over x squared, and in our last lesson we learned that if we rewrite this as 5 times x to the negative 2 power, then we can just use a basic rule. And that basic rule would be, okay, finding the derivative of 5 times x to the negative second would multiply the negative 2 with the 5 and get negative 10. And then the new exponent we would put on x would be the old exponent subtract 1. Well, that's negative 3. And then you can see, oh, well, now if we rewrite that without any negative exponents, we'll have the negative 10 times 1 over x to the positive 3 power. And clearly, that's exactly the result we got a moment ago, but in my estimation, in a much easier way, without as much conflict or trouble. So here's a case where we don't always have to use the quotient rule. On the next page, let's look at a couple more examples where we don't have to use the quotient rule. Okay, you see in this problem, f of x is equal to the fraction 2x cubed over 5, find f prime of x. And because this is a quotient, because this is a fraction, we can use the quotient rule. Okay, we can, but there is an alternate method. There is an alternate method in this case. I keep saying in this case because that's not always the situation. Sometimes there's not an alternate method. And this is similar to what we did last time. Here's what I'm going to do is I'm going to take the function f of x, and I'm going to notice that I could actually write that as 2/5 times x cubed. See, that's the same thing, isn't it? And when I notice that, then finding the derivative is relatively simple. Because the derivative we would multiply the 3 with the 2/5, that coefficient. I'm just going to say multiply this time without even trying to think of it in my head. And then we would reduce the exponent on x by 1, and so that would be an x squared. And then we really need to think about how do we multiply 2/3 and 3. We just multiply the 3 and the 2 together and get, oops, excuse me, that's a denominator of 5, my bad. Okay, so we multiply the 3 and the 2 and get 10/5 there, excuse me, 6/5 there. So we actually end up with f prime of x is equal to 6/5 times x squared. And we could even write that kind of back the way we did before. That is, we could write that as a 6x squared over 5, and either one of those answers would be acceptable. Okay, let's do another one quickly here. Given that y is equal to x squared minus 3x over x, find the derivative of y with respect to x. Now, once again, the quotient rule will work. It will work, but it's not required, again, in this case. And here's what I mean. Is if we look at that fraction, we can actually simplify it. Say, if we look at that fraction, we could say, I mean, there's more than one way for us to think of this. We could say, look, that fraction is x squared over x minus 3x over x. That's one way to think of that, about that. And of course, x squared over x is just x, and the 3x over 3 is just 3, and so we have nothing more than x minus 3. That's one way to think about it. Another way is that we could say, look, I think there's a common factor in the numerator of x. So in the numerator, we can factor it as x times x minus 3, and in the denominator, we have just an x, and so those will cancel, leaving just x minus 3. But nevertheless, what we have here, no matter how we look at this, where we are is we've simplified this to y is equal to x minus 3. So to find the derivative of y with respect to x, well, that's the derivative of x, which is just 1, minus the derivative of 3, which is 0. And so we have simply the derivative of y with respect to x is equal to 1. And it wasn't necessary to use the quotient rule because we could rework the function and use other techniques. On the next page, though, we'll see just the reciprocal of this function. And that will be a case where we have no other alternative but to use the quotient rule. Here you see that we have y is equal to x over x squared minus 3x, and we're to find the derivative of y with respect to x. So this is actually just the reciprocal of the fraction we had before. In this case, we must use the quotient rule. First, we can't break this fraction into two fractions because we don't add and subtract denominators. So we could not say, it would be incorrect to say that this is x over x squared minus x over 3x. That would be absolutely wrong because we don't subtract denominators. We only add or subtract numerators, and we do that when the denominators are the same. We could simplify, that's another way we did this a while ago. We could simplify this fraction, and we notice that in the denominator there's a common factor of x, and so we could factor it out and have x times x minus 3, and then we could cancel. And so we would end up with y is 1 over x minus 3. But again, we can't break this into two fractions. There's nothing else we can do here. We can't rewrite this as we have in the past. So now we have to use the quotient rule, okay, to find the derivative. Okay, so we begin that process. The derivative of y with respect to x is a fraction. And the way we go about calculating that is that we take the denominator, which is x minus 3, and we multiply it with the derivative of the numerator, which is just 1. And then we subtract from that. We go just the opposite, don't we? We say take the numerator, which is just 1, and multiply that with the derivative of the denominator. And of course the denominator is x minus 3, so that's a derivative we have to calculate. And then we divide all of this by the old denominator being squared, so x minus 3 squared. And now we go through the process of doing our calculations. So we have x minus 3. Oh, but the derivative of 1 is just 0 because 1 is a constant. Of course, we don't need 1 times anything, but I guess we can leave it there. The derivative of x minus 3, well, the derivative of x is 1 minus the derivative of 3, which is 0. So we just have a 1 in this position, and that's all divided by x minus 3 squared. And then we look back in the numerator and we recognize that, look, x minus 3 times 0 is just 0, because anything times 0 is 0. So we have a 0 in the beginning position minus 1 times 1 in the second position, all over x minus 3 squared. And then, of course, the numerator simplifies to negative 1, the denominator is just x minus 3 squared. Obviously, there's nothing to reduce there, so that's the resulting derivative. We're going to finish this quotient rule with a problem that's kind of similar to something we've done in the past, and that is, I think, to find the slope of a tangent line. Let's find the slope of a tangent line. We'll do that on the next page. So I misspoke. I've decided that what we're going to do is find the equation of a tangent line. So in this last problem about the quotient rule, we're to find the equation of the tangent line to the graph of y equal x squared minus 4 over 2x plus 5 at the x value of 0. Now remember, as we've done before, to find the equation of any line, we need the slope of the tangent line, or the line, and we need a point that is on the line. So let's first worry about the slope, okay? Slope of the tangent line. So we're just kind of getting our bearings here. The way we calculate the slope of the tangent line is we use the derivative. So it means we need to find the derivative. That's what the slope is going to be, is the derivative evaluated at the value of 0 for x. So that's the slope we're going to look for, and so that means that requires some work. It requires, before we know that slope, finding the derivative of y with respect to x. And we look above and say, oh, we're going to have to use the quotient rule. Okay, so let's just keep that in mind. Let's also realize that we need a point. So we need to use a point and the slope. So the point that we've got to worry about is when x is 0. Well, when x is 0, okay, here's what we know. The x value is 0. It's the y that we don't know. See, we don't know that y value, but we can calculate y from the formula. Remember, this point is the point of tangency. So not only is it on the tangent line, it's also on the graph of the function. Now we're thinking of it in terms of the tangent line, but to calculate y, we're thinking of it in terms of being on the graph of the function. So, pardon me, calculating y, we will put 0 in for x. We'll have 0 squared minus 4 over 2 times 0 plus 5, which ends up being simply negative 4/5. So this point that we're going to use for the equation of the line, tangent line, is 0, negative 4/5. And then remember what we're going to do after we have the slope, we have a point, we're going to use the form, it's actually called the point slope form, y minus y sub 1 is equal to m times x minus x sub 1. And remember, the m is something we've got to calculate after we find the derivative. See, after we find the derivative, we'll evaluate it at 0. And the x sub 1, oh, this is an x sub 1, getting in a hurry. The x sub 1 comma y sub 1 is the point that's on the tangent line and the graph, and that's the point 0, negative 4/5. So we'll come back to this after we do this calculation right here. Now, here's how we begin that calculation, of course. As we're finishing this, let's make sure we go through this in detail, because this is a complicated thing to do. Remember, we're thinking of our y as a fraction u over v. And the derivative of y with respect to x is also a fraction. It's the denominator of v times the derivative of the numerator, so that's u prime, minus the numerator, which is u, times the derivative of the denominator, which is v prime, and all that's divided by the denominator squared. So we can go back and do it through one little piece at a time, or we can go through this process as we've been doing, and actually kind of write it out as we go. That is, the derivative of y with respect to x. Well, the denominator is 2x plus 5. And that's going to multiply with the derivative of the numerator. There's a derivative of, and the numerator, of course, is x squared minus 4. We'll come back and calculate in a moment. Then minus the denominator, which is 2x plus 5. That's, excuse me, I'm sorry. Again, I'm getting in a hurry. It's the numerator, which is u, x squared minus 4, times the derivative of the denominator, derivative of, and the denominator is the 2x plus 5. So the lesson to learn here is even your teacher, when he gets in a hurry, he can make mistakes. So it's certainly not a good idea for you to get in a hurry. And then we'll take our old denominator, which is 2x plus 5, and we have to square it. Okay, well, let's make some room here. I kind of got that a little tight. So now we go through and calculate derivatives and replace them. So we have the 2x plus 5, and the derivative of x squared minus 4, I believe you'll agree, is just 2x. And then we have minus the x squared minus 4, and the derivative of 2x plus 5, I hope you'll agree, is just a 2. And of course we have a 2x plus 5 squared as our denominator. Now, as I've done before, well, maybe we can get away with this. I'm really going to think of this 2. Let's go to the next page. Okay, so on the next page, well, I have room here. The derivative of y with respect to x, as we look in this numerator, we need to multiply the 2x plus 5 and the 2x together, and so that's going to give 4x squared plus 10x, isn't it? Now, we also need to be careful that when we do the multiplication over here on the right, let's think about that 2 being in front. And so we're really multiplying with a negative 2, so we get negative 2x squared, and we get a positive 8, negative 2 times negative 4. And we still have divided by 2x plus 5 being squared. Now, on the next page, we'll simplify that numerator. So we have the derivative of y with respect to x is equal to, and I see that we've got a 4x squared and a minus 2x squared, which ends up just being 2x squared, doesn't it? So we have 2x squared, and we have a plus 10x and a plus 8, and that's all being divided by 2x plus 5 squared. Now, we might ask the question about, can we factor that numerator to simplify it, but kind of in a similar fashion to the way we discussed that last time. We would have to have a factor that had a 5 at the end to be able to do any reducing at all, because the only factors in the denominator have 5. And there's no way to get an 8 that will multiply with a 5. So there's no sense reducing, or no sense trying to reduce. But even more importantly than that in this case is, remember, we're just looking for a number. So we don't need to really, we're wanting the slope of the tangent line, and we don't really need to leave a derivative function. We need to have the value of the derivative when what was x going to be? X equals 0, right? And so that means we replace the x's, and we don't have to have it in simplified form. We replace the x's with 0. So that will give us what? It will be 2 times 0 squared plus 10 times 0 plus 8 in the numerator, and 2 times 0 plus 5 in the denominator squared. We'll see the result we get there. In the numerator, we'll just have an 8, won't we? And in the denominator, 2 times 0 is 0, plus 5 is 5, we'll have a 5 squared. And so we end up with just 8 over 25. Now remember, that's the slope of the tangent line. And we saw earlier that the point of tangency is 0, negative 4/5. So let's kind of summarize this. The slope is 8 over 25, and the point that we're talking about, we already calculated as 0 comma negative 4/5. So when we substitute into the y minus y sub 1 is equal to n times x minus x sub 1. We have y minus a negative 4/5. That's our y value, is equal to the slope, 8 over 25, times x minus our x value of the point, which is 0. So this becomes y plus 4/5 is equal to 8 over 25 times just x. X minus 0 is just x. So we subtract 4/5 from both sides. Okay, subtract 4/5 from both sides, and then this is the equation of said tangent line. Said tangent line. Well, this concludes our discussion about the quotient rule. Remember, it's a great tool. It's complicated. I suggest you write down the rule every time you're getting ready to use it, and then repeat using numerator-denominator words rather than U and V. Good luck to you.